In this video, we're going to look at a physical example of where second-order ODEs appear in the real world. So we're looking at a mechanical spring. We assume that there is a weight M that is hanging from a spring. Capital L is the displacement from the spring's resting position. So if there is no force applied to the spring ends at point L. And now we're going to add things to it, so the spring is going to be displaced from its normal resting position. What are the forces at play? The first is Hooke's law that states that there is, when you are looking at a spring, that it's away from the spring's resting position, then there is a force towards that resting position, and the force is determined by minus the displacement times k, where k is the spring's constant. And then there is the gravitational force. We have a mass, and that mass is pushed towards the center of the Earth by the gravitational constant. So F of g equals mg. Let's look at it a little bit at Hooke's law. If there was no mass attached to the spring would have a resting position. And if we move the spring away downwards towards the resting position, then the force is upwards towards the resting position. If we push the spring upwards away from the resting position, then the force is downwards towards the resting position. The direction of the force depends on the position you're in. What is the direction of the axis that we're looking at? So at L equal to 0, the spring is at its resting position. Is downwards L positive or negative, and is L upwards positive or negative? So what you want to think of is that the gravitational force is always downwards. And we decided to put a plus sign in front of that. So downwards is positive. That means that the order of the axis, you have L equal to 0 at the resting position, L positive underneath, and L negative on top of it. Now that we know this, we can look at the force that is applied to the mass hanging from the spring. You have in one direction, you have K of L, minus K of L, and you have M of G. In this case, well, you have forces applied to something that is hanging from the spring, so we can think of the fact that capital L, the displacement, changes over time. So we're introducing L as a function of time. But Newton's law of motion says that F equals m times a, where a is the acceleration. So a is the second derivative with respect to t of capital L. But the forces need to match. So we have to write ml second equals to F. So ml second equals to the force we just created, mg minus kl. Are there other forces? There is a damping force. It's a force that impedes movement, and it gets bigger the bigger the velocity. So the damping force is in the shape minus gamma times v, where v is the first derivative of L. So if we add this force to our already constructed equation, what we have is ml second equal mg minus kl minus gamma L prime. Another force, it's a very vague force that we're going to be introducing, is an external force. Is a function that a force that might depend on time that we can add. What is an external force? If you come and start pushing the spring, if there is a magnetic field that is interfering with your experiment, if there is noise, if the wall, the ceiling from which you're hanging is moving, all of these things are all bulged up into external forces. So now we have a second order ODE, non-homogeneous because we have the external forces happening there. And we have this mg coefficient. And we wonder if we can simplify it a bit. We can write our displacement as a function of time plus a constant. We can do that all the time. So the first and second derivative are equal to the first and second derivative of the function we just created, u, and we want to find this constant, so it would help us a bit. We plug this new ut plus c in the rule equation, and the only place in which it makes a difference is that kl becomes kut plus c. And we entangle this, and now we want to choose c such that the non-homogeneous terms that are not in the external force, so the non-homogeneous terms that we know, disappear. We choose c equals to mg divided by k. So now our ODE simplifies to mu second equals minus ku minus gamma u prime plus f of t. What are we thinking about? What is c in this situation? Well, we introduced L as being the resting position of the spring without the weight. But if you add a weight, then you're just resetting the resting position to another place that includes gravity. And this is what C is, the stretching of the spring due to gravity that would allow you to get to a new stable position. So now we have this equation, and we want to solve it. The first step we do is that we don't have any external forces and we don't have any dampening. So we just have mu second plus ku is equal to 0. We can solve with the characteristic equation mr squared plus k equal to 0. R is plus or minus square root of minus k divided by m. That is, it's imaginary. So the solution is a combination of sine of square root of k divided by m times t plus another constant, cosine of square root of k divided by m multiplied by t. Both of these terms are periodic and have this coefficient square root of k divided by m in front of the time. And we introduce this, we call it omega 0, and we call it the natural frequency. So if you have a mass hanging on a spring with no dampening, it will naturally get to a given frequency if you're not touching it. A linear combination of sine and cosine can be always rewritten as a coefficient called r times cosine of the frequency times t minus a shift. Sometimes that is useful because now we have cosine of something, and we know that cosine is always included between minus 1 and 1. So the coefficient in front of the cosine is the amplitude. It tells us how big the oscillations are. If you want to put it in a graph, what you have is, well, in the horizontal axis, we rescale the time with respect to omega 0. And we have a single wave that goes from minus r to r, and the first peak is at delta. This is an undampened oscillation. It will keep oscillating for all of infinity. What if we have no external forces, but we do have dampening? So gamma now is different than 0. We have mu second plus gamma u prime plus ku equal to 0. We associate it to its characteristic equation, mr second plus gamma r plus k equal to 0. And we solve for that. That makes us for r equals minus gamma plus or minus square root of gamma squared minus 4km divided by 2m. And depending on gamma and k and m, they're all three options. If gamma squared is bigger than 4km, we have two real roots. If gamma squared is equal to 4km, we have one unique root. And if we have gamma squared smaller than 4km, we have imaginary roots. What are these three options? The first one is gamma squared being very big, so the dampening effect is very strong. The other one, gamma is related to the other coefficients that we have. So gamma is not too strong, it's not too weak. while gamma squared being smaller than 4km means that the dampening is very light. So what we are expecting in this case is to have something very similar to what we had without dampening. So let's look into these cases. Real roots. We are always assuming gamma to be positive, by the way. We have gamma squared bigger than 4km. So we have R1 is equal to gamma minus something divided by 2m. That's obviously negative. While R2 is minus gamma plus square root of gamma squared minus something. We know that the whole gamma squared minus something is positive, but gamma squared minus something is obviously smaller than gamma squared. So minus gamma plus something that is smaller than gamma. That means that this is also a negative term. So both R1 and R2 are negative. So UT is a sum of negative exponentials. C1 exponential of minus absolute value of R1t plus C2 exponential of minus absolute value of R2 times t. Why am I putting the absolute values? Just to explicitly write down that these two values are negative, just to remind ourselves. So it's a sum of negative exponentials. It's going to behave roughly like a negative exponential. So wherever it starts, it's just going to go to zero very fast. In case of repeated roots, well, R1 is equal to R2 is equal to minus gamma divided by 2m. It's negative. So the solution is C1 plus C2 times t, exponential of something negative multiplied by t. So the solution will look like something that might have a bump, but after that it's going to zero for t tending to infinity. What happens for complex roots? Well, in this case, we have gamma squared minus 4km that is negative. If we write down everything that we have, is that we have the roots being minus gamma divided by 2m plus or minus imaginary number divided by 2m square root of 4km minus gamma squared. Now 4km minus gamma squared is positive, so that square root is positive as well. It's real. And in either case, the real part is negative. So the solution, if we introduce a new omega, that is this square root of 4km minus gamma squared, all of this divided by 2m, the solution is a combination of sine and cosine, depending on this new frequency that we just introduced, multiplied by a negative exponential. This means there are dampened oscillations. We can rewrite it as we did before. We rewrite the sine and cosine part as amplitude times cosine of frequency times minus delta. All of this times exponential of minus gamma divided by 2m multiplied by t. This means that our oscillations are bounded between something that is depending on time. They're bounded between plus and minus r exponential of minus gamma divided to m multiplied by t. And we can draw this, and between this we have the oscillations. So it tends to zero when time tends to infinity. This is what the dampening does. When it's very strong, you have something that tends to zero immediately. When it's not that strong, you have oscillations as we had in a non-dampened case, but the oscillations are decreasing in amplitude over time.